this is Mrs. Often, and here's our first lesson about rigid transformations. This lesson will introduce the idea of rigid transformations and discuss translations. Here we're talking about transformations of geometric figures in the coordinate plane. By the end of this lesson, you should be able to find the magnitude and direction of a translation. You should be able to describe a translation using coordinate notation or vector notation. And you should be able to describe what the three types of rigid motions are and what makes them rigid motions. Let's get started. So this is all part of transformations, and a transformation is an operation that maps a original figure, which is called a pre-image, onto a new figure called the image. On the graph to the left, this triangle ABC is the pre-image, and our second triangle, A prime, B prime, C prime, is the image. So those little apostrophes we read as prime. A transformation can change the position, orientation, or size of a figure. Now, when a transformation preserves the size and shape of a figure, we call that a rigid motion. All corresponding sides and angles of the pre-image and image are congruent. So we can see that triangle ABC is the same size and shape as the triangle image A prime, B prime, C prime. There are three rigid motions that we will study here: translations, a slide motion, reflections, a flip motion or a reflection across a line, and rotations, a spinning motion. Translations vertically or horizontally slide a figure. In coordinate notation, we see this as xy gets transformed x plus h, y plus k. Now it's important to remember that unlike function transformations, we're going to do exactly what it says. So this is not a situation where that plus h really means it's going to move to the left. No, it is going to move to the right. So when I look at my first example here, I have rectangle QRST with vertices at -6, -1, -3, -1, -1, -5, I'm sorry, -3, -1, 3, 1, 1, -5, and -2, -7. So there's my rectangle QRST. It's going to shift 5 units to the right and 7 units up. So each point is going to shift 5 units to the right and 7 units up. So it's going to look like this at the end, and let's see what that looks like. There's our QRST and our transform shape Q prime, R prime, S prime, T prime. Let's see those new coordinates. There they are, -1, 6, 2, 8, 6, 2, and 3, 0. Pause this video right now if you want to try it on your own with triangle CDE moving from 2, -1, 7, -4, and 4, -6 under the transformation x minus 3, y plus 8. If you've done this, you'll see that the translation looks like this and results in the following. To determine the new location, really all we need to do mathematically is subtract 3 from each x coordinate and add y plus 8, adding 8 to each y coordinate. Now, we can also work with vectors, and those will help us shift translations. Vectors are quantities that have both magnitude and direction. So it has direction and magnitude or size. A vector is represented in the coordinate plane by an arrow drawn from an initial point P to a terminal point Q. And the vector is denoted as PQ, read as vector PQ, has this little ray symbol on top. You do want to differentiate that from a ray, even though it will look like one. So vector PQ in the coordinate plane will look like this. The difference here is that unlike a ray, it is going to have a terminal point. It will stop at Q. Now the component form of a vector is written as PQ equals AB inside those triangle brackets. A is the horizontal component going this way, and B is the vertical component going this way. So if we think of this as being a right triangle, then we can determine the magnitude or the length of the vector by using the Pythagorean theorem to determine that length, C. Let's work with some vectors right now. We're going to name each of these vectors and then write the vector in its component form. So I have vector WV, and its component form, this vector goes over 1, 2, 9, and then up 3. Its component form would be 3. Its magnitude would be the square root of 9 squared plus 3 squared, and that's going to be 90, or 3 radical 10. Now this vector is going to the left and up. It's starting at B and has a terminal point at A, so it is vector BA. And it will have a component form of -5, 1. The magnitude of this vector will be the square root of 26. And lastly, we have vector SR. Vector SR is going to the left and down. It goes to the left 2, and then it goes down 10, so 11. So 2, -11, and that is a magnitude of square root of 125, or 5 radical 5. So our vectors have magnitude and direction, and as such, we can utilize them to translate figures. Let's see what this looks like. So we have triangle STU with vertices at -4, 2, 5, -1, and -2, 2. We're going to translate that according to the vector -1, -5. That is the same as having the component form x minus 1, y minus 5, or the coordinate form. So for this, we'll just subtract 1 and subtract 5, respectively, from the x and the y coordinates. So S prime is going to be located at -5, -3. T prime is going to be located at 4, -6. And U prime is going to be located at -3, -7. I can go ahead and graph that. There's S. And there's S prime. T. It's right here. And T prime is right here. And U is here. and u prime is right down here. What you'll notice is that if I draw vectors to connect each vertex to its translated vertex, all of those vectors should have the form -1, 5. And so I didn't graph S prime correctly. S prime should be over here. And the rest of these all have that vector of -1, -5. So we'll check that out. This is where S prime should be, not at this point. You can try doing trapezoid ABCD on your own and see that it does translate according to that vector. Okay. Finally, we want to be able to identify translations and write rules. We want to describe the translation that maps pre-image to image in coordinate notation and as a vector in component form. So I notice that I start here at point D and I end up here at point D prime. To get there, I'm going to go over 1, 2, 3, 4, 5, 6, 7 units to the right and 4 units up. There's my vector. So my vector is going to be 7, 4. And in coordinate notation, that's going to be xy, x plus 7, y plus 4. On my other figure, I'm using m and m prime. To get from m to m prime, I need to go horizontally to the left 4 units and then up 2 units. There's my vector. It is -4, 2. And my coordinate notation is xy, x minus 4, and y plus 2. So I hope that's been a helpful introduction to translations using coordinate and vector notation. Have a great day.